Imagine standing at the edge of a vast city at night, not in its glittering center, where neon pulses and life churns, but out there, where asphalt crumbles into dirt roads, where the last streetlights drown in darkness, and something else begins. Something old, something forgotten. Here, at the very boundary between light and void, we begin our descent into the Milky Way. This is not an ordinary journey. We won't fly from the galaxy's birth to its death, following time's arrow. No, we'll take a different path, spatial, anatomical. We'll start at the cold outskirts, where primordial silence reigns, and slowly, layer by layer, descend toward its burning heart. First stop, the halo, a spherical cloud wrapping the entire galactic disk like a ghostly veil. Here, in this vast emptiness, live the galaxy's most ancient inhabitants. Here lies a graveyard of worlds. The Milky Way's halo stretches about 200,000 light years from the center, nearly twice the diameter of the visible disk. Picture this. If the Milky Way were a coin lying on a table, the halo would be an invisible sphere the size of a basketball, with the coin suspended in its center. Invisible, but not empty. Through this darkness drift stars, not billions like in the disk, but merely 1% of the galaxy's total stellar mass. Here, stellar density is so low that the average distance between neighbors spans tens of light years. For context, our nearest stellar neighbor, Proxima Centauri, sits 4.24 light years away. Out here, that would be considered crowded. Imagine floating in an ocean where the nearest island is 10 times farther than the nearest island to you now, and you're already on an island in the middle of the Pacific. That's the halo. Cold, lonely, ancient. But this loneliness deceives, because each of these stars carries a story so old, it began before the Milky Way's disk even formed. In 2018, astronomers using the Gaia Space Telescope discovered a star with the unmemorable designation 2MASSJ 1808-2002-510437-8b. This red dwarf, just 14% the Sun's mass, dim enough to be invisible to the naked eye, turned out to be one of the oldest objects in our galaxy. Its age, 13.5 billion years. Let that settle for a moment. The universe is 13.8 billion years old. This star ignited just 300 million years after the Big Bang, before the first galaxies fully formed, before the cosmic dark ages ended, before there was such a thing as metal in the universe. When this star blazed to life, the Milky Way didn't exist. Not as we know it, anyway. There were no spiral arms, no ordered disk, no sun, no earth, no you. Just chaotic clouds of hydrogen and helium, collapsing under their own weight, beginning the long work of building a galaxy. This star predates its own home. These are called population 2 stars, ancient, metal-poor relics composed almost entirely of primordial hydrogen and helium. metallicity registers as Fe/H, less than -1.0, meaning they contain hundreds of times less iron than the Sun. They are witnesses. They remember the beginning. And here's what makes them stranger. Many of these ancient stars move on orbits that defy the galaxy's rotation. They fly at bizarre angles, cross the disk, venture far above and below. Their trajectories are chaotic, like shrapnel from an explosion, not orderly citizens following traffic laws. This is the first clue, the first hint that the halo isn't merely the galaxy's periphery. It's a museum of violence. In 1994, astronomers Rodrigo Ibata, Gerard Gilmore, and Mike Irwin were studying the sky when they noticed something strange. A long ribbon of stars encircling the Milky Way. Not a random scattering, a structure. They called it the Sagittarius Stream because its source, a small dwarf galaxy called Sagittarius, was being torn apart in real time. Here's what's happening. The Sagittarius dwarf galaxy orbits the Milky Way at a distance of just 70,000 light years. That's close. Close enough that our galaxy's gravity acts like a cosmic blender, ripping stars from Sagittarius with every pass. This has been going on for 3 billion years. Every orbit, more stars are stripped away. They stretch into a long ribbon, winding around the Milky Way like thread around a spool. If you could see this ribbon with your naked eyes, it would arc across the entire sky, a glowing scar made of millions of suns. Now imagine this. Each of those stars might have had planets. Some of those planets might have had oceans, maybe even life, simple, microbial, clinging to existence. And then one day, without warning, their star was ripped from its home galaxy and flung into orbit around a larger one. The planet wouldn't know. Life wouldn't know. The sky would look the same, but the star would never return home. That's what a stellar stream is, a river of exiles. And Sagittarius isn't the only victim. In 2018, astronomer Amina Helmi's team made a discovery that rewrote galactic history. Using data from the Gaia telescope, they found evidence of a cataclysmic collision that occurred 10 billion years ago, when the Milky Way was young, still forming, barely recognizable. A dwarf galaxy, later named Gaia Enceladus, after the Greek giant buried under mountains, smashed into the proto-Milky Way. The dwarf galaxy massed about 600 million suns. The proto-Milky Way, about 2 billion. The collision was apocalyptic. Gaia Enceladus struck the disk at an angle, like a fist through glass. The young Milky Way's disk shattered. Billions of stars were scattered into chaotic orbits. Gas clouds were heated, shocked, disrupted. Star formation shut down for hundreds of millions of years. The Milky Way nearly died in its infancy, but it survived. Over billions of years, the disk reformed. The chaos settled. Order emerged from violence. Yet scars remain. Right now, this very moment, tens of millions of stars, drift through the Milky Way's halo that once belonged to Gaia Enceladus. Their chemical fingerprints are different. Their orbits move backward. They refuse to join the galactic dance. They are ghosts, prisoners of war from a conflict that ended before Earth existed. And here's the unsettling part. This wasn't a rare event. The Milky Way has consumed at least 15 dwarf galaxies over the past 12 billion years. Some were tiny, a few million stars. Others, like Gaia Enceladus, were substantial. Each left a signature, a stream, a chemical trace, a population of stars moving the wrong way. Our galaxy is a cannibal, beautiful, majestic, spiral, and built from the corpses of its neighbors. What if you could see it? Close your eyes for a moment. Imagine this. You're standing on Earth, but you have magical eyes that can see not just visible light, but gravitational structures, dark matter, stellar streams, everything. You look up. The Milky Way is no longer a hazy band of light. It's a layered catastrophe. The disk glows white-blue, dense with stars, but wrapped around it, above, below, encircling, are dozens of faint ribbons. Stellar streams, each a different color, each tracing the death of a galaxy. The Sagittarius stream loops overhead like a glowing noose. The remnants of Gaia Enceladus form a ghostly haze throughout the entire sphere. Fainter threads crisscross the sky. Phoenix, Orphan, GD1, each a eulogy written in starlight. And beneath it all, invisible but felt, the dark matter halo, a vast sphere extending 10 times farther than anything visible, holding everything together with its gravity. If you could see this, the sky wouldn't be a peaceful scatter of stars. It would be a forensic diagram of murder. Every stream is a chalk outline. Every halo star is evidence. This is what we live inside. Now we arrive at the deepest mystery. If the halo contains just 1% of the galaxy's stellar mass, what holds these stars in their orbits? Why don't they drift away into intergalactic void? The answer arrived in the 1970s, courtesy of astronomer Vera Rubin. Rubin measured how fast stars were moving at various distances from galactic centers. According to Newton's laws, stars on the outskirts should orbit slowly, like Neptune crawling around the sun, compared to Mercury's swift lap. But that's not what she found. Stars at the galactic edge were moving just as fast as stars closer in. This shouldn't be possible, unless there's mass we can't see, a lot of it. Thus, dark matter. Today we know dark matter comprises about 85% of the Milky Way's total mass, roughly 1 to 2 trillion solar masses. Let me put that in perspective. All the stars you can see in the night sky, about 200 billion suns worth of mass. All the gas, dust, planets, black holes, everything visible, maybe 300 billion suns. Dark matter in the halo alone, over 1 trillion suns. It's not just that we live inside a galaxy. We live inside an invisible structure 10 times more massive than anything we can observe. and we only know it exists because its gravity keeps stars from flying away. Think of it this way. You're walking through a forest at night. You can't see the trees. No moonlight, no flashlight, nothing. But you keep bumping into them. You feel their bark. You hear wind in branches you cannot see. You smell pine, even though there's only darkness. That's dark matter. The Milky Way is a forest you cannot see, and we're walking through it right now. Every second, dark matter streams through your body, through this room, through Earth. It doesn't interact with normal matter except through gravity, so it passes through you like you're not even there. You are a ghost to it. It is a ghost to you. And yet, without it, the galaxy would fly apart. The stars would scatter. We wouldn't exist. We are alive because of something we cannot see, cannot touch, cannot understand. Meditate on that. But stars aren't the halo's only inhabitants. Drifting through the darkness are rogue planets, worlds ejected from their solar systems, now wandering alone through interstellar space. In 2011, a study estimated there could be 400 billion rogue planets in the Milky Way. That's twice the number of stars. Most are gas giants like Jupiter, flung out by gravitational chaos during their solar system's formation. But some are rocky, Earth-sized, maybe even Earth-like. Imagine one, a world that once orbited a sun, with continents and oceans, an atmosphere, perhaps even life. Then, billions of years ago, a close encounter with a larger planet, a gravitational slingshot, and suddenly it's moving too fast. It escapes its star's gravity and tumbles into the void. The oceans freeze within a few years, first the surface, then deeper, until even the seafloor is encased in ice kilometers thick. The atmosphere condenses and falls as snow, nitrogen snow, carbon dioxide snow, methane snow. Surface temperature, minus 270 degrees Celsius, just 3 degrees above absolute zero. But here's the remarkable part. If the planet is large enough and has enough internal heat from radioactive decay, there could still be liquid water beneath the ice. A subsurface ocean, heated from below, dark and isolated, but liquid. And where there's liquid water, there could be life. Not complex life, not dolphins or forests, but microbes, hardy, chemosynthetic organisms feeding on minerals and heat from hydrothermal vents, like the extremophiles at Earth's ocean floors. Life without sunlight, life in eternal night, life that doesn't even know it's orphaned. How many rogue planets harbor such hidden biospheres? How many frozen Earths drift through the halo, carrying entire ecosystems entombed in ice? We don't know, but they're out there. Billions of them. And every so often, one passes through our neighborhood, close enough to detect if we're looking, close enough to wonder what froze mid-breath when that world was cast into the dark. Let's return to stellar streams, Thanks to telescopes like Gaia, we've now catalogued dozens of these ghostly ribbons. The Phoenix Stream, a delicate thread of stars stretching 27,000 light years. Remnant of a dwarf galaxy destroyed billions of years ago. GD1, one of the longest, thinnest streams ever found. It stretches more than 60 degrees across the sky, but is barely 100 light years wide. In 2019, astronomers discovered something shocking. A gap in GD1, a section where stars simply aren't there. Something punched through it. The leading theory? A dense clump of dark matter, perhaps 1 million solar masses, tore through the stream like a bullet through fog, scattering stars and leaving a hole. A bullet made of invisible matter, fired by no one, from nowhere. The Orphan Stream, so named because we've never found its parent galaxy. The galaxy that created this stream has vanished so completely that no trace remains except the stream itself. It's a river without a source, a funeral without a body. Each of these streams is a tombstone, a monument to a galaxy that no longer exists. But they're not just relics, they're building materials. Over billions of years, these streams will disperse, their stars will scatter, their orbits will randomize, and eventually they'll become indistinguishable from the Milky Way's native population. The Milky Way isn't a single entity. It's a palimpsest, an ancient manuscript written over and over without erasing what came before. Beneath every star is the ghost of an older structure. Beneath every structure, the shadow of a devoured galaxy. Our home is a house built from bones. There's one more class of halo objects worth contemplating: white dwarfs. When a star like the Sun exhausts its fuel, it swells into a red giant, then gently sheds its outer layers into space, leaving behind a hot, dense core about the size of Earth. That's a white dwarf. No fusion, no burning, just cooling. A young white dwarf blazes at 100,000 degrees Celsius, hotter than any normal star's surface. But with no energy source, it can only radiate away what heat remains. After 1 billion years, 20,000 degrees Celsius. After 10 billion years, 5,000 degrees Celsius. After 100 billion years, barely glowing. After 1 trillion years, cold, dark. A black dwarf, a crystallized sphere of carbon and oxygen, essentially a diamond the size of a planet, floating in space, invisible. But here's the thing. Black dwarfs don't exist yet. The universe is only 13.8 billion years old, not nearly old enough for any white dwarf to have fully cooled. Even the oldest white dwarfs we've found still glow faintly, like coals from a fire that's been dying for 11 billion years. And some of those ancient white dwarfs live in the halo. By studying their temperatures, astronomers can measure the age of stellar populations. The cooler the white dwarf, the older the star that birthed it. In 2019, researchers discovered a white dwarf that's been cooling for 11 billion years.
meaning the star that created it formed just 2 to 3 billion years after the Big Bang. Think about what that means. That star burned when the universe was still an infant. It lived and died before the sun existed, before Earth, before anything you recognize. And now it's a dying ember, barely glowing, drifting through the halo. But it still whispers. If you could translate its faint infrared glow into sound, you'd hear it. I was here. I burned. I saw the beginning. In 1 trillion years, it will fall silent, a cold stone in the dark. But not yet.
If you stood in the halo and looked down at the galactic disk, you'd see something extraordinary. A thin, luminous plane stretching from horizon to horizon, studded with billions of stars, veiled in dark ribbons of dust. It would look like the edge of a colossal wheel, slowly turning, but you're not part of that wheel. Halo stars don't participate in the disk's rotation. They move chaotically, elliptical orbits at steep angles, some even retrograde, flying backward relative to the galaxy's spin. They're not bound by the disk's rules. They're refugees, exiles, survivors. The average orbital period for a halo star, about 500 million years, twice as long as the Sun's 225 million year galactic year. They take their time. They have eternity. Stellar density in the halo is so sparse, the average distance between neighbors spans 50 to 100 light years. Imagine living on a planet orbiting a halo star. Your night sky would be almost empty, a handful of dim stars scattered across blackness. The Milky Way, the disk, would appear as a faint glowing band, beautiful but remote. You would feel the silence, the weight of distance. But you wouldn't be in emptiness. You'd be in a forest you couldn't see, dark matter trees holding you in place, invisible roots binding the galaxy together. And if you waited, really waited, hundreds of millions of years, you'd see the disk breathe. It pulses up and down, warps like vinyl in the sun, ripples from ancient collisions that haven't finished propagating. The galaxy is alive, not biologically, but structurally, dynamically. It moves, it breathes, it eats, and we're inside it. Amid the halo's darkness are globular clusters, spherical swarms of stars, so dense they resemble balls of light. These clusters contain anywhere from 100,000 to several million stars, packed into regions just 100 to 200 light years across. In their cores, stars are separated by just 0.1 to 1 light year, 10 times closer than the Sun and Proxima Centauri.
If Earth orbited a star in a globular cluster's core, your night sky would be ablaze. Thousands of stars, brighter than Venus. No true darkness, just perpetual twilight, bathed in the light of countless suns. Imagine never seeing night. Imagine a sky so crowded with light that shadows have shadows. The Milky Way has about 150 globular clusters, most in the halo, orbiting at distances of 20,000 to 100,000 light years. They're old, many over 12 billion years, nearly as old as the universe itself. And here's the strange part. Some globular clusters may not be clusters at all. They might be the cores of cannibalized dwarf galaxies, the dense hearts that survived when everything else was torn away. Take Omega Centauri, the brightest globular cluster in the Milky Way's halo. It contains 10 million stars and masses roughly 4 million suns. But its stars have different chemical compositions, multiple generations, different metallicities. That shouldn't happen in a normal cluster. Unless Omega Centauri was once the core of a dwarf galaxy. It had its own disk, its own rotation, its own history. Then the Milky Way devoured it, stripped away the outer stars, shredded the disk, left only the core. Now it orbits in silence, a kingdom reduced to a city reduced to a glowing graveyard. But still shining, still remembering. The halo isn't just stars and dark matter. It's also a storm of invisible particles, cosmic rays, high-energy protons, and atomic nuclei accelerated to near light speed by supernova shocks, pulsar winds, and black hole jets, stream through the galaxy constantly. Right now, about 10,000 cosmic rays are passing through your body every second. You don't feel them. They cause no pain, but they're there. Ghostly bullets fired by dead stars, traveling for millions of years, passing through planets, oceans, people, as if we're made of air. In the halo, their density is lower, but they're still present. An invisible sea of energy, carrying information from the galaxy's most violent events. And then there are neutrinos. Neutrinos are even more ghostly. They barely interact with matter at all. Every second, 100 trillion neutrinos from the sun pass through your body. You don't notice. A neutrino could pass through a light year of solid lead and have only a 50-50 chance of hitting one atom. They're born in fusion reactions, supernova cores, black hole accretion disks. They escape from places light cannot, from the centers of stars, from collapsing cores, from the event horizons of the universe's most extreme objects. Right now, neutrinos from the supernova that seeded our solar system's formation 4.6 billion years ago are still flying through space. Some are passing through you. Some were born in the cores of stars belonging to Gaia and Enceladus 10 billion years ago, before that galaxy was destroyed. They carry memories of worlds that no longer exist. You can't see them. You can't touch them. But they're here, whispering stories in a language we'll never fully understand. Stop. Breathe. We're standing at the galaxy's edge. The halo. Ancient, ghostly, silent. Around us drift elder stars older than the Milky Way itself. Ribbons of dead galaxies loop overhead. Rogue planets wander in eternal night. White dwarfs cool into diamonds. Dark matter holds everything in an invisible embrace. There's almost no light here, but it's not empty. It's filled with memory, history, violence. The halo is the foundation, the graveyard, the museum. It's where the Milky Way stores its crimes. Every star here is evidence, every stream a confession. Our galaxy is beautiful, but it's also a predator. It built itself from the wreckage of smaller galaxies. It's still growing, still consuming. Right now, this very second, gravity is tearing stars from Sagittarius, adding them to the halo's collection. In a few billion years, Sagittarius will be gone. Just another stream, another ghost. And here's a revelation you need to sit with. You are made of this. Every atom in your body, carbon, oxygen, nitrogen, iron, was forged in stars. Some of those stars belong to Gaia Enceladus, to Sagittarius, to nameless dwarf galaxies devoured before Earth existed. You are made from the wreckage of dead galaxies. Your bones are stardust from a cannibal's feast. Every breath you take is an echo of ancient violence, but also ancient creation. Because without those collisions, without those deaths, the heavy elements necessary for life wouldn't exist. The Milky Way wouldn't have grown massive enough to birth the solar system like ours. You are alive because galaxies died. This is the paradox of the halo. It's a graveyard, but it's also the soil from which we grew. And now that we've stood in this silence, felt the weight of deep time, understood the invisible architecture holding us together, we're ready to descend deeper, to where stars are born, to where chaos pretends to be order, to the spiral arms. But before we go, look up one last time. Imagine you can see it all. The streams of dark matter, the ancient stars, the rogue planets, the white dwarfs glowing faintly like dying coals. This is where we came from. This is the house we live in. A house built from alien bones. A house still growing, still hungry, still beautiful. Now, descend. There's something we haven't talked about yet. Something that happens on timescales so vast that civilizations rise and fall between breaths. The galactic disk breathes, not metaphorically, literally. The disk oscillates, expanding and contracting vertically, like lungs filling and emptying with air. Scientists call this the breathing mode of the galactic disk. Here's how it works. Imagine the disk as a membrane, a thin sheet of stars, gas and dust held together by gravity. When something disturbs it, a satellite galaxy passing nearby, an asymmetry in mass distribution, even the collective motion of millions of stars, the disk responds. It ripples. Waves propagate through it, causing the entire structure to thicken and thin rhythmically. The amplitude is small,
maybe 200 to 300 light years of vertical motion. But the disk is so vast that this creates enormous flows of matter. Gas rises above the plane, cools, falls back down. Stars bob up and down with it. The period of one breath, roughly 80 to 100 million years. Think about what that means. The last time the disk exhaled, mammals had just begun to diversify after the dinosaurs' extinction. Whales were still walking on land. Grasses hadn't yet evolved. One breath, and you're experiencing a tiny fraction of one inhalation, frozen in time, imperceptible except through careful measurement of stellar velocities. The galaxy breathes, and we're riding the breath. But the disk doesn't just oscillate gently, it also erupts. When massive stars explode as supernovae in dense clusters, especially in the spiral arms, their combined shock waves don't just heat the surrounding gas. They blast it out of the disk entirely. Multiple supernovae exploding in the same region over a few million years create what astronomers call a superbubble. A vast cavity of million-degree plasma, hundreds of light years across. This bubble is lighter than the surrounding cool gas, so it rises up through the disk into the halo, like a hot air balloon. Eventually, thousands of light years above the galactic plane, the gas cools, condenses, and falls back down like rain. This is called the galactic fountain. Matter cycles, disk to halo to disk, over and over. The time scale? About 100 to 200 million years per cycle. We've detected these fountains using radio telescopes, mapping the motion of neutral hydrogen. We see vast arcs of gas rising from active star-forming regions in the disk, climbing into the halo, then falling back down. The galaxy doesn't just breathe, it fountains. It circulates matter between its layers, mixing chemical elements, transporting energy, maintaining a dynamic equilibrium. And here's the remarkable part. Some of the atoms in your body right now, carbon, oxygen, nitrogen, might have been part of a galactic fountain billions of years ago. Forged in a supernova in the disk, blasted into the halo, cooled and fell back into a molecular cloud, incorporated into a new star, then into a planet, then into you. You're made of recycled stardust, literally. Now we need to talk about something most people don't know. The Milky Way isn't just a spiral galaxy. It's a barred spiral. At the very center of the galaxy, hidden behind thick clouds of dust that block visible light, is a massive, elongated structure called the galactic bar. It's roughly 27,000 light years long and about 5,000 light years thick. It's made of billions of older, redder stars, packed densely together, rotating as a solid unit. Not like the differential rotation of the disk,
but like a rigid rod spinning in place. The bar completes one rotation about every 100 to 120 million years. And it's powerful. The bar's gravity reshapes the entire inner galaxy. It funnels gas inward toward the galactic center, feeding the central black hole. It perturbs stellar orbits, creating resonances that reinforce the spiral arm structure. In fact, the spiral arms might owe their existence to the bar. Without it, the arms might be less pronounced, more chaotic, harder to maintain. The bar is like a cosmic mixer, stirring the inner galaxy, driving gas flows, regulating star formation. But here's the eerie part. We didn't know about the bar until the 1990s. For decades, astronomers thought the Milky Way was a regular spiral galaxy. Then infrared telescopes, which can see through dust, revealed the bar's existence. We've been living inside a barred spiral for billions of years, and only recently figured it out. Because we're inside, looking out, trying to see the forest while standing among trees. And that raises a question. What else don't we know? What other massive structures exist in the galaxy that we haven't detected yet because of our vantage point, our limitations, our blind spots? The answer, almost certainly, is many. The galaxy is more complex than we realize. Always. You might think stellar streams, those ghostly ribbons of stars from destroyed galaxies, only exist in the halo. But you'd be wrong. Some exist in the disk, too. These are different. They're not from external galaxies being devoured. They're from dissolved star clusters, open clusters, groups of hundreds or thousands of stars born together from the same molecular cloud, gradually disperse over hundreds of millions of years. Gravitational interactions with passing clouds, tidal forces from the galaxy, close encounters with other stars, all of these slowly pull clusters apart. The stars don't disappear. They spread out along the cluster's original orbit, forming a stream, a river of stars, all moving together, all siblings, but no longer bound. We've discovered dozens of these streams in the solar neighborhood. One passes right through our region of the galaxy, a stream of stars from a cluster that dissolved 300 million years ago. Some of those stars are now closer to Earth than Proxima Centauri. They're our neighbors, former siblings scattered by time. And we didn't know they were related until we measured their velocities and chemical compositions and realized they're moving together. They share the same birthplace. The galaxy is filled with invisible relationships. Stars that look unrelated are actually family, separated by time and distance, but still connected by origin. It's like discovering that random strangers on a subway were all born in the same hospital. The galaxy remembers connections we've forgotten. Look at a picture of a spiral galaxy seen edge-on. You'll notice something striking. Dark bands cutting across the bright disk. Those aren't empty spaces. They're dust lanes. Regions where interstellar dust is so thick it blocks light from stars behind it. Dust grains are tiny, typically about 0.1 micrometers across, smaller than the wavelength of visible light. They're made of carbon, silicates, and ice, forged in the atmospheres of dying stars, ejected into space, now drifting through the interstellar medium. Individually, they're insignificant, but collectively, they're powerful. A single dust grain can scatter starlight, redirecting it. A cloud of dust grains can absorb starlight entirely, converting it to infrared radiation, heat. The result: vast regions of the galaxy are invisible in optical light, but infrared telescopes see through dust, and what they reveal is stunning. The dust lanes aren't voids, they're nurseries. The densest, darkest regions, where visible light can't penetrate, are where molecular clouds exist. Cold, dense, collapsing, forming stars. The darkest places in the galaxy are the brightest in infrared, because that's where creation happens. Darkness isn't absence, it's potential. The spiral arms look bright in visible light because of young, hot stars. But in infrared, the dark lanes between the arms light up, glowing with the heat of protostars, planetary disks, molecules excited by starlight. The galaxy has two faces. One we see with our eyes, bright arms, dark lanes. One we see with infrared, bright lanes, dim arms. Neither is the truth. Both are partial views. The galaxy is more than the sum of wavelengths. Let's descend into one. A giant molecular cloud, GMC, one of the largest structures in the galaxy. These clouds can be millions of solar masses, spanning hundreds of light years. They're the largest gravitationally bound objects in the Milky Way, besides the galaxy itself.
Inside it's cold, 10 to 20 Kelvin, just a few degrees above absolute zero, and dark. So dark that if you were inside, even with a powerful flashlight, you'd see nothing but blackness. The dust is so thick that light can't penetrate more than a fraction of a light year. You'd be surrounded by silence, no stars visible, no external light, just cold, dark, dense gas pressing in from all sides. But you'd also sense something: gravity. These clouds are unstable. Gravity is slowly winning against gas pressure. The cloud is contracting, slowly, imperceptibly, but inevitably. In some regions, the contraction is accelerated. Clumps have formed, dense cores, each the mass of a few suns, collapsing faster now. In a few 100,000 years, they'll ignite. Stars, dozens, hundreds, maybe thousands, depending on the cloud's mass. But for now, it's just potential, waiting, compressing, heating. This is where most stars in the galaxy are born, inside giant molecular clouds, hidden from view, collapsing in darkness. The clouds themselves are shaped by the spiral arms. Compression from density waves triggers their formation, concentrates them in the arms. But once formed, they live for tens of millions of years, long enough to drift partway through the arm before dispersing. Some molecular clouds form stars quickly, within a few million years. Others linger for 20,
30, even 50 million years before collapsing. Why the difference? Magnetic fields, turbulence, support from internal motions. The clouds are fighting gravity, and sometimes they win for a while. But eventually, gravity always wins. Massive stars, those born with 20, 50, 100 times the sun's mass, burn with ferocious intensity. Their cores are so hot, their fusion so rapid, that they exhaust their hydrogen in just a few million years. The sun will burn for 10 billion years total. A 50 solar mass star? 3 million years. It's born, lives, and dies faster than a mountain erodes. And its death is violent.
When the core runs out of fuel, it collapses in less than a second. The rebound creates a shockwave that tears the star apart, a supernova. For a few weeks, that single exploding star outshines its entire galaxy. Then it fades, leaving behind either a neutron star, a city-sized ball of matter so dense a teaspoon weighs 1 billion tons, or a black hole. But here's the tragedy. These massive stars are the engines of chemical evolution. Inside their cores, they forge carbon, oxygen, nitrogen, silicon, iron, all the elements necessary for planets and life. When they explode, they scatter those elements into space, enriching the interstellar medium, seeding future generations of stars with the raw materials for planets. Without massive stars, there would be no rocky planets, no oceans, no life. But they burn so fast. They exist for such a brief moment, cosmically speaking, that they barely have time to influence their surroundings before they're gone. They're martyrs, born to die. And in dying, they give the universe everything it needs to make worlds like Earth. Every atom of iron in your blood was forged in a dying star's core. Every atom of calcium in your bones, every atom of oxygen you're breathing right now, all of it, stardust, supernova ash. You are the debris of stellar explosions. Think about that next time you feel insignificant. You're made of the rarest, most precious material in the universe. Heavy elements, forged in stars that burned bright and died fast, so that you could exist. When massive stars are born, they don't appear alone. They form in groups called OB associations, clusters of hot, massive O and B type stars, often numbering in the dozens or hundreds. These aren't tightly bound like globular clusters. The stars are loosely associated, spread over regions 100 to 500 light years across. But they're related, born from the same giant molecular cloud, siblings, and their combined radiation is devastating. Dozens of massive stars, all emitting torrents of ultraviolet light, create what's called an H2 region, a bubble of ionized hydrogen gas glowing at 10,000 degrees Celsius. These regions are beautiful. The Orion Nebula is an H2 region. The Eagle Nebula, home at the famous Pillars of Creation, is an H2 region. The Carina Nebula, the Tarantula Nebula, all H2 regions. They glow red and pink in photographs, the signature color of ionized hydrogen recombining with electrons. But inside they're hellish. Radiation so intense it would strip away a planet's atmosphere in a few thousand years. Stellar winds moving at 2,000 kilometers per second. Shockwaves from supernovae compressing gas, triggering secondary star formation in surrounding clouds, a cascade effect. OB associations don't just create stars, they reshape the interstellar medium. They carve cavities in molecular clouds, blow bubbles in the gas, trigger and suppress star formations simultaneously. They're agents of chaos and creation. And they don't last long. Within 10 to 20 million years, the most massive stars explode. The remaining stars drift apart, dissolving into the general stellar population. The association disperses, but its effects linger for hundreds of millions of years. Bubbles of hot gas slowly expanding, compressed shells of gas forming new stars, chemical enrichment spreading through the disk. OB associations are brief, but influential, like revolutions. Here's something astronomers still argue about. How long do spiral arms last? Are they permanent features maintained by density waves for billions of years? Or are they transient, forming, persisting for a few 100 million years, then dissolving, only to be replaced by new arms? The answer seems to be both. The large-scale spiral pattern, the 2 or 4 major arms, is maintained by density waves and reinforced by the central bar. Is relatively stable over billions of years. But individual segments of the arms, the bright, star-forming regions, are transient. They flare up when gas is compressed, triggering a burst of star formation. They fade when the gas is exhausted or blown away by stellar winds and supernovae. New segments form, old segments disperse. The arms are persistent patterns made of transient events. Like a fountain, the shape of the fountain, the arc of water, is stable, but the water itself is always moving, always being replaced. The spiral arms are the same, stable structures made of moving parts, and we're caught in the current. There's a deeper layer of structure we haven't discussed. Resonances. Resonances occur when the orbital period of stars matches the rotation period of the spiral pattern in specific mathematical ratios. At these locations, called Lindblad resonances, strange things happen. Stars get trapped. Their orbits lock into step with the spiral pattern, creating stable configurations. The result? Stars accumulate at these resonances, reinforcing the spiral structure. There are typically 2 major resonances. Inner Lindblad resonance, ILR, inside the corotation radius, where stars orbit faster than the pattern. Outer Lindblad resonance, OLR, outside corotation, where stars orbit slower than the pattern. At these resonances, stars don't just pass through the arms, they linger. And lingering means more time in dense regions, more interactions, more gravitational perturbations. For gas clouds, this means compression. For planetary systems, this could mean disruption.
Resonances are structurally important but potentially dangerous. The Sun, fortunately, orbits near the corotation zone between the major resonances. We're in a stable orbit, not trapped in resonance. Lucky, again. Because resonances can be chaotic zones, regions of enhanced gravitational turbulence, where orbits become unstable over long timescales. We avoided that, by chance, or perhaps not by chance.
Perhaps planetary systems that form in resonance zones don't survive long enough to develop life. Perhaps the only civilizations that emerge are those, like us, lucky enough to orbit in the quiet zones. This is called the galactic habitable zone hypothesis. Not just the right distance from the galactic center, not just the right position relative to spiral arms, but the right orbital resonance, the right place in the galaxy's invisible musical structure. We're alive because we're in tune. Close your eyes. Feel the ground beneath you. You're standing on a planet orbiting a star. That star is moving at 828,000 kilometers per hour around the galactic center. Right now, you're traveling faster than you can imagine, and you don't feel it. The Sun is also bobbing up and down through the galactic plane, oscillating like a buoy on ocean waves. And the entire disk, this vast structure of 200 billion stars, is breathing, flexing, warping under gravitational influences from satellite galaxies. The spiral arms you see in photographs aren't solid. They're waves, patterns, temporary concentrations of matter moving at their own speed, independent of the stars. Stars drift in, slow down, light up, then drift out. The arms persist, but they're not made of the same stars from moment to moment. It's like standing in a river. The river has a shape, but the water is always moving. You can't step in the same river twice. The galaxy is the same. You're moving through invisible structure, density waves, magnetic fields, resonances that shape your existence without you ever knowing. Your very survival depends on being in the right place, not just on Earth, not just around the Sun, but in the galaxy, in the right spiral arm, in the right orbit, in the right resonance zone. Everything is structure, and you're swimming through it, blind, trusting that the currents will carry you safely. And so far, they have. For 4.5 billion years. Open your eyes. You're still here, still moving, still alive. Because the galaxy, vast, chaotic, violent, has allowed it. For now, we've seen enough. The stellar nurseries, beautiful and brutal. The molecular clouds, dark towers where stars are born. The massive stars, burning bright and dying fast, seeding the galaxy with elements. The spiral arms, illusions of permanence, waves of probability, traffic jams in space. The interstellar medium, an ocean of gas and dust, roiling with energy. The galactic fountains, matter cycling between disk and halo. The bar at the center, hidden, powerful,
shaping the entire inner galaxy. The breathing disk, oscillating, flexing, alive. We've learned that structure is temporary, that patterns persist while their components change, that we're alive because of cosmic architecture we can barely perceive. And now, we move inward to the one place in the galaxy that's genuinely stable, the one region where chaos gives way, temporarily, to order. Our neighborhood, the quiet harbor, the place where, against all odds, a small rocky planet was allowed to cool, form oceans, develop an atmosphere, and nurture life for billions of years. Home. We've been descending home through the ancient halo, graveyard of galaxies, realm of ghosts, through the spiral arms, beautiful illusions, waves of creation and destruction. Now we arrive at the place that matters most, not because it's special in any cosmic sense, not because the galaxy cares about it, but because it's ours, a pocket of relative calm in a violent universe, a quiet eddy in the galactic current, a place where, for 4.6 billion years, a yellow dwarf star has orbited peacefully, dragging with it a collection of planets, asteroids, comets, and on one of those planets, us. This is the Orion Spur, also called the Orion Arm, also called the Local Arm, a minor spiral structure, not one of the galaxy's major arms, but a bridge between them, a side street, a suburb. And it's perfect, not by design, by accident, by luck, by the improbable arrangement of gravity, timing, and chaos that allowed a planetary system to form and persist long enough for complexity to emerge. Welcome home. Let's understand what that means. The Orion Spur stretches about 10,000 light-years in length and roughly 3,500 light-years in width. It's not a major arm like Perseus or Sagittarius Carina. It's a spur, a smaller branch connecting larger structures, possibly a fragment left over from an earlier spiral pattern, possibly triggered by gravitational disturbances from the bar. Astronomers still debate its exact nature, but here's what we know. It sits between the Perseus arm, about 6,500 light-years farther from the galactic center, and the Sagittarius Carina arm, about 6,500 light-years closer in. The Sun orbits roughly 26,000 to 28,000 light-years from the galactic center, right in the middle of this spur. And that position matters, because the major arms, Perseus, Sagittarius Carina, Scutum Centaurus, are sites of intense star formation, massive stars, frequent supernovae, high radiation, OB associations blasting their surroundings with ultraviolet light. Not ideal for life. But here in the spur, things are quieter, fewer massive stars, lower supernova rate,
less radiation, more stability. The Orion Spur is like living in a small town between two major cities, close enough to benefit from the resources and infrastructure, far enough to avoid the noise, traffic and danger. We're in the Goldilocks zone, not just of our solar system, but of the galaxy. And we didn't choose this. We were born here, by chance. But even the quiet harbor has scars. We live inside a cavity, a vast, roughly spherical region of space, about 1,000 light years across, filled with hot, low-density gas. It's called the local bubble, and it was carved by supernovae about 10 to 20 million years ago. Recent, cosmically speaking, a cluster of massive stars in our neighborhood reached the end of their lives and exploded, one after another. Each supernova created a shockwave, expanding outward at thousands of kilometers per second, sweeping up gas and dust, compressing it into a dense shell at the bubble's edge. The interior was left nearly empty, just thin, hot gas at about 1,000,000 degrees Celsius, too hot to collapse and form stars, too diffuse to block light. A cavity. And the sun, along with hundreds of thousands of other stars, happens to be inside it. We're living in the aftermath of stellar violence. The bubble isn't static, it's still expanding, though much more slowly now. The shockwave has cooled, decelerated, but the structure remains. If you could see X-rays, you'd see the bubble glowing faintly, a ghostly shell of hot plasma surrounding the sun. Inside, we're relatively safe. The density of interstellar gas is lower than in surrounding regions, which means fewer collisions with dense clouds, less gravitational perturbation, fewer hazards. The local bubble is, paradoxically, a safe space created by explosions. We're alive inside a scar. Let's zoom out and establish exactly where we are. The Sun's position in the galaxy, distance from galactic center, approximately 26,000 light years, plus or minus 1,000. Distance above galactic plane, approximately 60 light years, and rising. Orbital velocity, approximately 828,000 kilometers per hour, approximately 230 kilometers per second. Galactic year, one complete orbit, approximately 225 to 250 million years. Vertical oscillation period, approximately 70 million years, crossing the plane every approximately 35 million years. Location, Orion's spur between Perseus and Sagittarius Carina arms. Special zone, near the corrotation radius, where stellar orbital speed matches spiral pattern rotation speed. That last point is critical. We're in corrotation. This means we don't frequently cross through spiral arms. Most stars do. They orbit faster or slower than the spiral pattern, so they enter and exit arms repeatedly over their lifetimes. But the Sun's orbital speed is nearly synchronized with the rotation speed of the spiral pattern. We stay roughly the same distance from the major arms. this is incredibly lucky, because crossing through spiral arms means exposure to higher densities, more gravitational perturbations, more massive stars, more supernovae. It's dangerous, but we avoid it. We're in a stable orbit, moving in step with the galaxy's large-scale structure, a cosmic safe zone. And we've been here, in this general region, for billions of years, long enough for Earth to form, long enough for oceans to stabilize, long enough for life to emerge, evolve, complexify, long enough for you to be here, reading this, aware of your place in the architecture. In the 2000s, astronomers began asking a new question. Is there a galactic habitable zone? We know about the habitable zone around stars, the region where a planet can have liquid water. But what about around the galaxy itself? Are there regions of the Milky Way where life is more likely to emerge, where planetary systems are more likely to survive long enough for complexity to develop? The answer increasingly seems to be yes. The galactic habitable zone depends on several factors. Metallicity. You need enough heavy elements to form rocky planets. Too close to the galactic center, and metallicity is too high, leading to massive planets that destabilize systems. Too far out, and metallicity is too low, preventing rocky planet formation. Supernova rate. Too close to the center, or inside major spiral arms, and the supernova rate is dangerously high. A nearby supernova, within 30 light years, could strip away Earth's ozone layer, exposing the surface to lethal radiation. Spiral arm crossings. Regions that frequently cross through spiral arms experience gravitational perturbations that can destabilize planetary orbits, send comets into the inner solar system, trigger mass extinctions, orbital stability. Resonances with the bar or spiral pattern can create chaotic zones where orbits become unstable over long timescales. Taking all of this into account, the galactic habitable zone is an annulus, a ring-shaped region between about 20,000 and 30,000 light years from the galactic center. The Sun orbits at approximately 26,000 light years, right in the middle. Again, lucky, or perhaps not luck. Perhaps the only civilizations that survive long enough to ask these questions are those born in the habitable zone. Selection bias. We're here because we could be here. Anywhere else and we wouldn't have made it. Let's talk about our star. The Sun is a G-type main sequence star, spectral class G2V. Mass, 1 solar mass. Obviously, it's the definition. Radius, approximately 696,000 kilometers. Surface temperature, approximately 5,500 degrees Celsius. Core temperature, approximately 15 million degrees Celsius. Age, approximately 4.6 billion years. Remaining lifespan, approximately 5 billion years. It's ordinary, spectacularly ordinary. About 90% of stars in the galaxy are less massive than the Sun. Only about 10% are more massive. In terms of stellar demographics, the Sun is slightly above average, bright enough to provide stable energy for billions of years, but not so massive that it burns out quickly. It's a Goldilocks star, not too hot, not too cold, not too massive, not too dim, just right. And its stability, its ability to burn hydrogen at a steady rate for 10 billion years, is why Earth has had a stable climate long enough for life to evolve. Variable stars, stars whose brightness fluctuates, would make life nearly impossible. Imagine if the Sun's output varied by 10% over decades or centuries. Earth would swing between ice ages and scorching heat, never allowing ecosystems to stabilize. But the Sun is boring, reliable, predictable. It's been burning steadily for 4.6 billion years, with luminosity variations of less than 1% over timescales relevant to life. That's the kind of star you want if you're trying to build a biosphere. Not spectacular, just consistent. Remember, the Sun doesn't just orbit smoothly in the galactic plane. It oscillates vertically. Right now, we're about 60 light-years above the midplane, moving upward at about 7 kilometers per second. In roughly 15 million years, we'll reach maximum height, about 230 light-years above the plane, then fall back down. We'll cross through the midplane in about 30 million years, then plunge to 230 light-years below it, then back up. This oscillation has a period of about 70 million years. Why does this happen? The galactic disk has mass. That mass exerts gravity, pulling stars toward the midplane. When a star crosses the plane, it doesn't stop. It overshoots, pulled by its own momentum. Then gravity pulls it back. It's like a spring or a pendulum. The result, all stars in the disk bob up and down through the plane, crossing it periodically. And here's the disturbing possibility. Some scientists have proposed that when the Sun crosses through the dense midplane, where gas, dust, and debris are most concentrated, Earth experiences increased comet impacts. The idea, gravitational perturbations from dense regions shake the Oort cloud, a vast shell of icy bodies surrounding the solar system at distances of 50,000 to 100,000 astronomical units, sending comets into the inner solar system. More comets leads to more impacts, leads to mass extinctions. There's some controversial evidence that mass extinctions on Earth occur with a periodicity of roughly 26 to 30 million years. This matches roughly half the vertical oscillation period, the time between plane crossings. Correlation, coincidence, causation, we don't know. But the idea is haunting. Mass extinctions might be written into our galactic orbit. The death of the dinosaurs 66 million ago, asteroid impact. But what shook that asteroid loose from the Oort cloud? Perhaps we were crossing the galactic plane. Perhaps our position in the galaxy, something we never feel, never see, shaped the history of life on Earth. Evolution driven by galactic mechanics. Within 30 light-years of the Sun, there are about
450 known stars. Most are red dwarfs, small, dim, long-lived. A few are sun-like. A handful are white dwarfs, stellar remnants. One is a binary system with a neutron star. The nearest star, Proxima Centauri, 4.24 light-years away, a red dwarf, part of the Alpha Centauri system. The nearest sun-like star, Tau Ceti, 11.9 light-years away. The nearest young star, Beta Pictoris, 63 light-years away. Not in the 30 light-year radius, but close enough to matter. A star just 20 million years old, still surrounded by a protoplanetary disk. These stars are our neighbors. Some move with us, part of the same local group, born from the same general region of the galaxy. Others are just passing through, stars on different orbits that happen to be nearby at this moment in time. In 100,000 years, the night sky will look different. Stars will have moved. New stars will enter our neighborhood. Old neighbors will drift away. The constellations we know, Orion, the Big Dipper, Cassiopeia, are temporary arrangements. They look fixed, but they're not. They're snapshots of a dynamic system, frozen in the brief moment of human history. In 1,000,000 years, no constellation will be recognizable. The stars will have scattered. New patterns will emerge. And whoever, whatever is looking up from Earth, if anything is, will see a completely different sky. The heavens are not eternal. They're just slow. In recent years, astronomers using the Gaia satellite discovered something remarkable. Many of the sun's neighbors aren't randomly distributed. They're organized into streams, groups of stars moving together through space, sharing the same velocity, the same trajectory. These are the remnants of dissolved star clusters, groups of stars born together billions of years ago, now spread out along their original orbit. One such stream passes right through the solar neighborhood. It contains dozens of stars within 300 light-years of the sun, all moving in the same direction, all born from the same molecular cloud about 1 to 2 billion years ago. We didn't know they were related until we measured their velocities with extreme precision. Now we see the pattern. They're siblings, scattered by time and tidal forces, but still connected by origin. And here's the question. Is the sun part of a stream? Did it have siblings, stars born from the same cloud 4.6 billion years ago, that have since drifted away? The answer is probably. When the sun formed, it likely formed in the cluster of hundreds or thousands of stars. But that cluster dispersed within 100 million years, and those siblings scattered throughout the galaxy. Some might be nearby, unrecognized. Others might be thousands of light years away. We might never identify them, but they're out there. Stars that share the sun's exact age, chemical composition, birthplace. Strangers who are family, lost in the crowd.
Even here, 26,000 light years from the center, we're not isolated. The galaxy breathes, and we feel its breath. There's a wind blowing outward from the galactic center, the galactic wind, driven by supermassive black hole activity, supernova explosions, and stellar winds from millions of massive stars in the inner galaxy. This wind is tenuous, just a few atoms per cubic centimeter, but it's moving fast, hundreds of kilometers per second. It carries energy. It carries material, gas enriched with heavy elements from supernovae in the inner galaxy, spreading outward into the disk. It carries information, chemical signatures, isotope ratios, traces of events that happened thousands of light years away and millions of years ago. We're bathed in this wind constantly. It shapes the interstellar medium in our neighborhood, influencing star formation, sculpting molecular clouds, carrying seeds of elements that will one day be incorporated into new stars. Some of the atoms in your body, carbon, nitrogen, oxygen, came from the galactic wind, forged in stars near the galactic center, blown outward by supernovae and stellar winds, eventually incorporated into the molecular cloud that collapsed to form the Sun, then Earth, then you. You're made of galactic wind, literally, atoms that traveled halfway across the disk to reach you. We're also swimming through dark matter. The local dark matter density, the amount of dark matter in the solar neighborhood, is estimated at about 0.3 to 0.4 giga-electron volts per cubic centimeter. That translates to roughly 1 proton's worth of dark matter per 3 cubic centimeters. It sounds like nothing, but dark matter doesn't interact with normal matter except through gravity. So even though it's diffuse, its cumulative gravitational effect is enormous. The dark matter in the solar neighborhood contributes to the overall gravitational potential of the galaxy, helping to keep the Sun in its orbit, stabilizing the disk, preventing stars from drifting away. Without dark matter, the galaxy would fly apart. The Sun would escape into intergalactic space. We owe our existence to an invisible substance we can't detect directly. Every second, trillions of dark matter particles pass through your body. You don't feel them. They don't interact with your atoms, but they're there, holding the galaxy together, keeping the Sun in orbit, allowing Earth to exist. We're alive because of ghosts, cosmic rays, high-energy particles accelerated by supernova shocks and other violent events, constantly bombard the solar system. In interstellar space, the cosmic ray flux is about 1 particle per square centimeter per second. That's higher than near Earth, because Earth's magnetic field and the Sun's solar wind deflect many cosmic rays, creating a protective bubble called the heliosphere. But in the broader solar neighborhood, outside the heliosphere, cosmic rays are everywhere. They're ionizing radiation. They can damage DNA. In space without shielding, they're lethal over long timescales. But they also serve a purpose. Cosmic rays ionize the interstellar medium, creating charged particles that couple to magnetic fields, driving turbulence, regulating star formation. They're a background hum of energy, always present, always influencing, always shaping the environment. And they carry information. By studying the energy spectrum and composition of cosmic rays, we can learn about supernova rates, stellar populations, magnetic field structures, events and structures far beyond our immediate neighborhood. Cosmic rays are messengers, envoys from distant catastrophes, and they're passing through you right now. Thousands per second, invisible rain from exploding stars. And then there are neutrinos. Trillions pass through your body every second. Most come from the sun, byproducts of fusion in its core. But others come from farther away, from supernovae in the galaxy, from cosmic ray interactions in the atmosphere, from the Big Bang itself, the cosmic neutrino background, though we haven't detected it yet. Neutrinos barely interact with matter. A neutrino could pass through a light year of solid lead and have only a 50% chance of hitting an atom. They're ghosts, but they're also windows, because neutrinos escape from places light cannot, from the cores of stars, from collapsing supernovae, from the event horizons of black holes. They carry information from the universe's most extreme environments. Every second you're bathed in a neutrino sea, a flood of particles carrying messages from events you'll never witness, from places you'll never see. You are transparent to them. They are invisible to you, but you're connected by neutrinos, by cosmic rays, by the galactic wind, by dark matter. You're not isolated. You're embedded in a web of invisible interactions, stretching across the galaxy, connecting you to everything. Pools. We've descended from the halo to the spiral arms, to here, the solar neighborhood, 26,000 light years from the galactic center. In the Orion Spur, a quiet minor arm. In the local bubble, a cavity carved by ancient supernovae. In corotation, moving in step with the spiral pattern, avoiding frequent arm crossings. In the galactic habitable zone, the right distance, the right metallicity, the right environment. Orbiting a stable, ordinary, boring star. Bobbing gently through the galactic plane on a timescale so long it's irrelevant to human history. Surrounded by a few hundred neighbor stars, most of them dim and distant. Bathed in cosmic rays, neutrinos, galactic wind, dark matter. This is home. Not because it's special, but because it's survivable. Because by chance or selection bias, it's the kind of place where a planetary system can form and persist long enough for life to emerge. Most of the galaxy is not like this. Most of the galaxy is too close to the center, too much radiation, too many supernovae, too much chaos. We're too far out, too little metallicity, too few heavy elements, too cold. Or in major spiral arms, too much gravitational perturbation, too many massive stars, too unstable. Or in resonance zones, chaotic orbits, long-term instability.
Most of the galaxy is hostile. But here it's quiet. For now. And that for now is important. Because nothing is permanent. The galaxy is changing. The spiral pattern is evolving. The sun is moving. In a few 100 million years, we might drift out of corotation, start crossing through spiral arms more frequently. In a few billion years, the Milky Way will collide with Andromeda, reshaping everything. The quiet harbor is temporary, but temporary is all life needs. 4.6 billion years of relative stability, enough for Earth to cool, for oceans to form, for life to emerge, for evolution to complexify. Enough for you to be here, aware, asking questions, understanding your place in the structure. That's the miracle. Not that Earth exists, but that it existed long enough, that the galaxy allowed it, that chaos, by accident, created a pocket of calm.
And in that calm, something extraordinary happened. Atoms organized into molecules, molecules into cells, cells into organisms, organisms into complexity, complexity into awareness. And now, 13.8 billion years after the Big Bang, a small part of the universe has become conscious of itself. You, made of stardust, born in a quiet harbor, alive because of architecture, aware because of time. That's what this chapter is about. Not the galaxy's grandeur, but its mercy. The brief, fragile mercy that allowed us to exist. Let's end by looking up. From Earth, the Milky Way appears as a hazy band of light, arcing across the sky, visible only from dark locations, away from city lights. That band is a galactic disk, seen edge on. We're inside it, looking outward along the plane. The densest, brightest part of the band is toward the constellation Sagittarius. That's the direction of the galactic center, 26,000 light years away. We can't see the center in visible light, too much dust, but infrared and radio telescopes reveal what's hidden. A dense cluster of stars, the central bar, the supermassive black hole. In the opposite direction, toward the constellation Auriga, the band is fainter. That's the outer galaxy, less dense, fewer stars. Above and below the band, we see stars of the local neighborhood, the nearest few thousand stars, scattered through the local bubble, and beyond them, far beyond, the halo, invisible to the naked eye, but there, surrounding everything. This is our view, not from outside, looking down at a majestic spiral, but from inside, looking out through layers of structure, seeing only fragments of the whole. We're like fish in an ocean, trying to understand the ocean. We can't see the shore. We can't see the surface. We're submerged, embedded, swimming through something too vast to comprehend from within. But we try, we measure, we map, we model. And slowly, piece by piece, we're assembling a picture of the structure we live inside. The Milky Way is not just our home, it's our context. the framework within which everything we know exists. And understanding it means understanding ourselves, where we came from, why we're here, how long we have. We've lingered in the quiet harbour long enough. We've seen why this place allowed us to exist. The right distance, the right orbit, the right stability. But there's one place we haven't visited yet. The place that holds everything together. The place where the rules change. Where gravity becomes so strong that time itself bends. Where stars orbit at thousands of kilometers per second, packed so densely they occasionally collide. Where a supermassive black hole, 4 million times the sun's mass, sits dormant, waiting. The galactic center, the eye of the storm, the heart of the beast. It's time to descend. We've come a long way. From the cold ancient halo, graveyard of galaxies, realm of elder stars. Through the spiral arms, beautiful illusions, waves of creation and destruction. Past the quiet harbor, our temporary refuge, 26,000 light years from the center. Now we make the final descent, inward, to the place where everything changes, where the galactic disk compresses into a dense nuclear bulge, where millions of stars orbit in a space smaller than the distance between spiral arms, where a massive bar of ancient stars rotates like a cosmic propeller, funneling gas toward the center. And at the very heart, invisible, inevitable, inescapable, sits Sagittarius A star, a supermassive black hole, 4 million times the mass of the Sun, compressed into a region smaller than Mercury's orbit. This is the galactic center, the eye of the storm, and it's nothing like home. As we descend past 10,000 light years from the center, something shifts. The disk, relatively flat and orderly in the solar neighborhood, begins to thicken. Stars become more densely packed. The vertical scale height increases from about 1,000 light years in the disk to several thousand light years here. We're entering the nuclear bulge, a roughly spherical concentration of old red stars surrounding the galactic center. This is ancient territory. Most stars here are 10 to 12 billion years old, born when the galaxy was still forming, before the disk fully settled. They orbit chaotically, not in the ordered rotation of the disk, but in random, elliptical paths, some prograde, some retrograde, some plunging radially inward before swinging back out. It's like the halo, but dense. In the solar neighborhood, the average distance between stars is about 5 light years. Here, it's less than 1 light year. In some regions, closer to the center, it drops to 0.1 light years or less. If you lived on a planet in the nuclear bulge, your night sky would be ablaze with thousands of stars brighter than Venus. No darkness, just perpetual twilight, pierced by the light of ancient suns. But you wouldn't want to live here. Too much radiation, too many close encounters, too much chaos. The nuclear bulge is not a place for life. It's a place for survival, for stars old enough and stable enough to endure the violence. Now, at about 5,000 light years from the center, we encounter something remarkable. A massive structure invisible from Earth in optical light,
hidden behind thick dust clouds. The galactic bar, a rotating, elongated concentration of stars, roughly 27,000 light-years long, 5,000 light-years thick, extending outward from the galactic center like the arms of a cosmic clock. It's made of billions of older stars, red giants, evolved stars, some of the galaxy's earliest stellar generations, all rotating together as a nearly solid structure. Not like the disk's differential rotation, but like a rigid bar spinning in place. The bar completes one rotation every 100 to 120 million years, and its gravitational influence is enormous. The bar funnels gas inward.
As gas orbits in the disk and encounters the bar's gravitational field, it loses angular momentum, slows down, and spirals inward toward the center. This feeds the galactic center with fresh material, sustaining star formation in the central molecular zone, and occasionally feeding the supermassive black hole itself. The bar also shapes the spiral arms. Resonances between the bar's rotation and the disk's rotation create density waves that propagate outward, forming and maintaining the spiral structure we see. Without the bar, the Milky Way's spiral arms would be weaker, more transient, less defined. The bar is the architect, the unseen conductor, orchestrating the galaxy's large-scale structure. And we only discovered it in the 1990s. Think about that. We've been living in a barred spiral galaxy for billions of years and didn't know it until 3 decades ago. Because we're inside, looking through dust, trying to map a structure we're embedded in. It's humbling, a reminder that we still don't see the whole picture. Within 1,500 light-years of the center lies a region unlike anywhere else in the galaxy. The Central Molecular Zone, CMZ. Here, the density of molecular gas is 10 to 100 times higher than in the spiral arms. The temperature is higher, 50 to 100 Kelvin, compared to 10 to 20 Kelvin in typical molecular clouds. The pressure is higher, the turbulence is higher, everything is more intense. This should be a star formation paradise. High density plus high temperature plus abundant gas equals stars. But something strange is happening. The CMZ is underperforming. Given the amount of gas and the conditions, astronomers expected intense star formation, rates 10 to 100 times higher than observed. But the actual star formation rate is surprisingly low. Why? The leading hypothesis: turbulence and magnetic fields. The CMZ is so turbulent, gas moving at tens of kilometers per second in chaotic supersonic flows, that it's hard for gravity to win. Magnetic fields thread through the gas, providing additional support against collapse. The result: the CMZ is a frustrated star factory. It has all the ingredients, but the conditions are so extreme that star formation is suppressed. Gas swirls, heats, compresses, but doesn't collapse. Not easily, anyway. Occasionally conditions align. A shock wave from a supernova or stellar wind compresses a cloud enough to overcome turbulence. A gravitational instability triggers collapse. and a burst of star formation occurs. Brief, intense, then quenched. This creates a unique stellar population. Young, massive stars coexist with ancient red giants. Star clusters form, then are torn apart by tidal forces within a few million years. The CMZ is a place of extremes. Too hot, too dense, too chaotic for stable, sustained star formation. But occasionally, violently productive. Near the galactic center, within 100 light-years, are two of the most remarkable star clusters in the Milky Way, the Arches cluster and the quintuplet cluster. Both are young, just 2 to 4 million years old. Both contain dozens of massive stars, 20 to 100 times the Sun's mass, packed into regions just a few light-years across. The Arches cluster is the densest known young star cluster in the galaxy. About 150 massive stars in a region less than 1 light-year across. Stellar density over 100,000 times higher than the solar neighborhood. If you were in the Arches cluster, the nearest star might be just 0.01 light-years away, about 1,000 astronomical units, less than the distance to the Oort cloud. The night sky would be terrifying. Dozens of brilliant stars, each brighter than Sirius, scattered across the sky. No darkness, just blazing light and radiation. The combined ultraviolet output from these massive stars is so intense it ionizes surrounding gas for dozens of light years. But these clusters are doomed. Tidal forces from the galactic center are already tearing them apart. Stars at the cluster's edge are being stripped away, forming tidal tails, streams of escaping stars. Within 10 to 20 million years, the clusters will be completely dissolved. Their stars will scatter throughout the central region, and the clusters will cease to exist. They're beautiful, brilliant, and temporary, like fireworks, bright, intense, brief, then gone. At the very center, within 30 light-years of Sagittarius A star, lies the nuclear star cluster, NSC. This is one of the densest stellar environments in the galaxy. About 25 million stars, packed into a sphere just 30 light-years across. Average stellar density, over 1 million times higher than the solar neighborhood. In the densest regions, within 1 light-year of the center, stellar density exceeds 100 million stars per cubic light-year. Stars are separated by light weeks, not light years. If the Sun were in the nuclear star cluster, the nearest star might be just 0.001 light-years away, about 60 billion kilometers, 10 times the distance to Neptune. Close, dangerously close. At these densities, close encounters between stars are common. Gravitational interactions can strip away planets, destabilize orbits, eject objects into interstellar space. Binary stars collide and merge. Stars occasionally fall into the central black hole. The nuclear star cluster is a place of constant violent interaction. And yet, it's also ancient. Many of the stars here are old, 10 billion years or more. They've survived in this environment for most of the galaxy's history, orbiting the black hole, dodging neighbors, enduring. But there are also young stars, massive, hot, blue stars, less than 10 million years old, orbiting within light weeks of Sagittarius A star. How they form there is a mystery. Stars shouldn't be able to form that close to a supermassive black hole. Tidal forces should prevent it. Leading hypothesis, they formed further out and migrated inward. Or they formed in a dense disk of gas that briefly existed around the black hole.
We don't know, but they're there. Young stars in the shadow of a black hole, living on borrowed time. At the exact center of the galaxy sits an object we cannot see directly. Sagittarius A star, pronounced Sagittarius A star. A supermassive black hole. Mass, approximately 4 million solar masses. Size, roughly 44 million kilometers across, about 0.3 astronomical units, smaller than Mercury's orbit around the Sun. It's invisible, no light escapes, but we know it's there because of what it does to the stars around it. For decades, astronomers have tracked the orbits of stars near the galactic center, particularly a group of stars labeled S stars, S1, S2, S62, etc. These stars orbit incredibly fast. S2, for example, completes one orbit around Sagittarius A star in just 16 years. Its closest approach, Periastron, brings it to within 17 light hours of the black hole, about 120 astronomical units, roughly the distance from the Sun to the outer edge of the Kuiper Belt. At that distance, it's traveling at nearly 3% the speed of light, about 8,000 kilometers per second. This is one of the fastest moving stars we've ever observed, and its orbit is extremely elliptical, shaped like a stretched out cigar, not a circle. By tracking S2 and other S stars over decades, astronomers have precisely measured the mass and position of the central black hole. It's there, invisible but undeniable, a gravitational monster holding the galaxy's core together. But here's the strange part. It's quiet. Sagittarius A star is not actively feeding. It's not consuming large amounts of material. It's dormant. Occasionally, maybe once every few thousand years, a gas cloud or unlucky star wanders too close and gets shredded, causing a brief flare of radiation. But most of the time, the black hole is silent, waiting. This wasn't always true. In 2010, astronomers analyzing data from the Fermi Gamma-ray Space Telescope discovered something astonishing. Two enormous bubbles of gamma-ray emission extending above and below the galactic plane.
Each bubble stretches about 25,000 light-years from the galactic center, reaching halfway to the Sun's orbit. They're symmetrical, perfectly aligned with the galactic rotation axis, and they glow with high-energy radiation. These are the Fermi bubbles, and their scars, evidence of a massive outburst from the galactic center, either from Sagittarius A star or from intense star formation activity. that occurred roughly 6 to 9 million years ago. Here's what probably happened. The black hole accreted a large amount of gas, perhaps from a disrupted star or a dense molecular cloud. As the gas spiraled inward, it heated to millions of degrees, emitting intense radiation and driving powerful winds outward. These winds blasted through the galactic disk, plowing into surrounding gas, creating shock waves that expanded into enormous bubbles. Then the outburst ended. The black hole went quiet again. But the bubbles remained, still expanding, still glowing faintly with the energy of that ancient event. This tells us something important. Sagittarius A star is not always dormant. It has periods of activity, brief, violent episodes when it consumes matter and erupts with energy. During these episodes, it could have been a quasar, a brilliant beacon of radiation visible across the universe. And someday, it might wake up again. Now and then, the black hole does something remarkable. It flings a star out of the galaxy entirely. Here's how. A binary star system, two stars orbiting each other, wanders too close to Sagittarius A star. The black hole's gravity captures one star, pulling it into a tight orbit. But the other star is ejected, catapulted outward at incredible speed, thousands of kilometers per second, fast enough to escape the galaxy's gravity entirely. These are called hypervelocity stars. We've discovered dozens of them. Stars traveling at 500 to 1,000 kilometers per second, racing toward intergalactic space. Some are already beyond the galactic disk, out in the halo. In a few million years, they'll leave the Milky Way entirely, drifting into the void between galaxies. The refugees, exiles, cast out by the black hole's violence, and they'll wander forever. No galaxy to call home, just darkness. Imagine being on a planet orbiting a hypervelocity star. You'd watch your galaxy, the Milky Way, shrink in the sky over thousands of years. Eventually, it would become just another spiral among billions. Then, too distant to resolve. Then, invisible. You'd be alone in intergalactic space. No neighbors, no structure, just a single star fleeing into the void. It's beautiful and tragic, a casualty of the black hole's gravity. Let's ask the dangerous question. What would happen if the black hole became active? If a massive gas cloud or disrupted star fell into Sagittarius A star, triggering an accretion event, the black hole would light up. As matter spiraled inward, it would heat to billions of degrees, emitting X-rays, gamma rays, intense ultraviolet radiation. The galactic center would become a blinding beacon, an active galactic nucleus, possibly a quasar. For a brief time, decades, centuries, maybe millennia, the Milky Way would be one of the brightest galaxies in the universe. And here on Earth, 26,000 light years away, we'd see it
Not immediately. Light takes 26,000 years to reach us. But eventually, our night sky would change. The direction of Sagittarius, currently just a faint haze of stars, would brighten. A brilliant, point-like source of light would appear, brighter than any star, perhaps brighter than the full moon, bright enough to cast shadows at night. And that light would be dangerous. High-energy radiation, X-rays, gamma rays, would flood the galaxy. Most would be absorbed by the interstellar medium long before reaching Earth. But some would get through. Enough to ionize the upper atmosphere. Enough to damage the ozone layer, possibly. Enough to increase radiation at Earth's surface. Not enough to sterilize the planet,
but enough to cause stress, increase mutation rates, potential disruption to ecosystems, a mass extinction, unlikely from this distance, but a noticeable event, yes. The good news, Sagittarius A star shows no signs of imminent feeding. The bad news, these events can happen suddenly, triggered by unpredictable disturbances. We're probably safe. Probably. But the black hole is there, waiting. Here's a paradox of the galactic center. It's the most chaotic place in the galaxy. Stars orbiting at thousands of kilometers per second. Extreme densities, intense radiation. A supermassive black hole. Frequent supernovae. Tidal disruptions. And yet, it's also the most stable place in the galaxy, because everything here is bound by the black hole's gravity. Stars orbit rapidly, but their orbits are stable, shaped by the black hole's massive gravitational well. The nuclear star cluster has existed for billions of years. The bar has rotated steadily for billions of years. The galactic center is violent, but predictable, chaotic but ordered. It's like standing in the eye of a hurricane. Wind howls all around, but at the center, there's stillness, calm. A strange, oppressive calm created by the very thing that drives the chaos. The black hole is the center of everything, the anchor, the conductor. Without it, the galaxy would lose cohesion. The bar would dissolve. The spiral arms would weaken. The galaxy might fragment or disperse. The black hole, this invisible monster, is what holds the Milky Way together. It's not a destroyer, it's a keystone. Remove it, and everything collapses. Within a few light years of Sagittarius A star, there are stars that defy explanation. Young, massive stars, O and B types, less than 10 million years old. They're arranged in a disc-like structure, orbiting the black hole. This shouldn't be possible. Tidal forces from the black hole should prevent star formation this close. Gas clouds should be torn apart before they can collapse. Yet these stars exist. Leading theories. They formed farther out and migrated inward, captured by gravitational interactions with other stars or the black hole itself. They formed in a dense accretion disk that briefly existed around the black hole during a feeding episode millions of years ago. They're the remnants of a merged star cluster
whose core was destroyed by tidal forces, but whose individual stars survived. We don't know, but they're there. Young, brilliant, doomed, orbiting so close to the black hole that their lifetimes, already brief for massive stars, are further shortened by the extreme environment. In a few million years, they'll explode as supernovae, or be torn apart by tidal forces, or fall into the black hole. They're temporary, like everything here. But for now, they shine, defiant, inexplicable, beautiful. Imagine it. You're floating above the galactic center. Below you, a maelstrom. Millions of stars swirling in chaotic orbits around an invisible center. Gas clouds streaming inward, glowing with radiation from newborn stars. The galactic bar rotating slowly, funneling matter toward the core. The nuclear star cluster, dense, ancient, blazing with the light of 25 million suns. And at the center, nothing, just darkness, a black hole, invisible, inevitable, holding everything together through gravity alone. You can't see it, but you feel it. In the orbits of stars moving impossibly fast, in the way gas spirals inward, accelerating as it falls, in the structure of everything, the bar, the spiral arms, the disk, the halo. Everything is shaped by the center. Everything orbits the abyss. And yet, from 26,000 light years away, we see almost none of this. Dust blocks visible light. We map the center in infrared, radio, X-rays. We infer the black hole's presence from stellar motions. We're blind to most of what's happening, but we know it's there. The heart of the galaxy. The place where everything begins and ends. The eye of the storm. And standing here, floating above it, you realize this is what holds our galaxy together. Not the stars, not the gas, not the spiral arms. A black hole, an absence, a void. 4 million suns worth of mass compressed into nothing. And around it, 200 billion stars dance. Sagittarius A star is dormant now, but it won't stay that way forever. In about 4 billion years, the Milky Way will collide with the Andromeda galaxy. The two galaxies will merge. Gas will be funneled inward. Star formation will spike. And both central black holes, Sagittarius A star and Andromeda's black hole, about 100 million solar masses, will be fed. They'll light up, brilliant quasars visible across the universe. And eventually, the two black holes will merge, creating gravitational waves so powerful they'll ripple through space-time, detectable by civilizations billions of light years away, if any exist. The result, a single massive black hole, perhaps 100 million solar masses. At the center of a new galaxy, neither Milky Way nor Andromeda, but something new. Milkomeda, some call it. A giant elliptical galaxy. Quiet, old,
stable. The spiral arms will be gone. The disk will be disrupted. Most stars will be scattered into a vast, diffuse halo. The sun, if it still exists, will be flung into the outer regions, far from the new galactic center. Earth, if it survives, will see a completely different sky. No Milky Way band, no spiral structure, just a faint, diffuse glow from the merged galaxy's core. And at the center, a supermassive black hole, dormant again, waiting for the next meal, the next outburst, the next era of violence. Galaxies don't die, they transform, they merge, they evolve, and the black holes at their centers grow, waiting for eternity. Here's the final paradox. The smallest thing in the galaxy, the singularity at the heart of Sagittarius A star, infinitely small, infinitely dense, controls the largest structure. The black hole's event horizon is just 44 million kilometers across. Tiny, a speck. But its gravity shapes the orbits of stars hundreds of light years away. Its influence extends throughout the entire galaxy, stabilizing the bar, reinforcing the spiral arms, regulating gas flows. The smallest controls the largest. The invisible shapes the visible. The abyss defines the structure. And we, 26,000 light years away, orbiting a quiet yellow star in a minor spiral arm, owe our existence to it. Without Sagittarius A star, the Milky Way would be different, less structured, less stable, perhaps not capable of supporting long-lived planetary systems like ours. We're alive because of a black hole, an object that destroys everything it touches, but from a distance, creates, shapes, organizes, allows. Think about that. The most destructive object in the galaxy is also the reason we exist. We've reached the end. From the halo, ancient, cold, filled with ghosts, we descended. Through the spiral arms, beautiful illusions, waves of creation, past the quiet harbor, our temporary home, fragile and fortunate, to the center, chaotic, violent, held together by an invisible monster. This is the Milky Way, not a static structure, but a living, breathing, evolving system, built from the wreckage of smaller galaxies, shaped by density waves, magnetic fields, dark matter, held together by a supermassive black hole. And within it, somewhere in the quiet suburbs, far from the violence, a small blue planet orbits a yellow star. On that planet, atoms organized in the molecules, molecules into cells, cells into organisms, organisms into awareness. And now, 13.8 billion years after the Big Bang, a small part of the universe looks up at the rest and understands. You are made of stardust, born in a galaxy built from wreckage, alive in a quiet pocket of chaos.
aware because the universe allowed it for a brief, improbable moment. You are the Milky Way, looking at itself. Atoms forged in supernovae, organized into complexity, asking questions about origin and fate. That's the miracle. Not that galaxies exist, but that within them, meaning emerged. Awareness, wonder, you. One last thought. Imagine you're on a planet in the Andromeda galaxy, 2.5 million light years away. You look up at the night sky, and there, faint, diffuse, barely visible, is a small spiral galaxy, the Milky Way. From that distance, you'd see the whole structure, the spiral arms, the central bar, the bulge, the halo, all of it laid out before you like a photograph. You'd see what we can never see from inside, the forest, not the trees. And you'd think, beautiful, ordinary, just another spiral galaxy among billions. You wouldn't know that within it, on a small rocky planet, orbiting an unremarkable star, something extraordinary happened. Life, awareness, civilization. You wouldn't know that beings on that planet are looking back at you, wondering the same things. Are we alone? Is there meaning? Why does the universe allow complexity? The galaxies don't care. They spin, merge, evolve, indifferent to the life within them. But we care. We look up. We ask questions. We map the invisible. We tell stories about our place in the structure. And maybe, just maybe, someone in Andromeda is doing the same, looking at the Milky Way, wondering. Two galaxies hurtling toward collision. Two civilizations asking the same questions, separated by 2.5 million light years, connected by curiosity, by wonder, by the improbable fact that we exist at all. That's where the story ends, not with answers, but with questions, not with certainty, but with awe. We live in a galaxy built from wreckage, held together by darkness, shaped by invisible forces. And within it, for a brief moment, we shine, not as bright as the stars, but bright enough to see, bright enough to wonder, bright enough to understand, however imperfectly, our place in the cosmic architecture. That's enough. That has to be enough, because it's all we have, and it's beautiful. We've traveled from the cold edges where galaxies die to the burning heart where darkness holds everything together. You are made of this journey, atoms forged in distant supernovae, scattered by galactic winds, assembled by chance into awareness. Tonight, when you look up at the Milky Way stretching across the sky, remember, you're not looking at your home. You're looking through it, from inside. A small part of the galaxy that learned to see itself.
May you carry this perspective gently, the knowledge that you're temporary, but made of ancient things, small but built from starlight, alone but connected to everything. The universe allowed you to exist for a brief, improbable moment. That's enough. Safe travels through the spiral.